Yes. Yeah. Okay, so the recording has started and
the full screen.
I try.
No.
Okay, good. Okay.
Yeah.
Is the microphone?
It's a microphone. What if I put it like this? Is that?
Yeah,
Okay.
sure.
This seems to work. Well, hello everybody, and hello everybody online. My name is Christian Junker Jansen. I'm a senior researcher at Aarhus University in Denmark. And I'm here to give you an update of the dust-related work that we do in our department. Some of you have seen a few of the slides before, so I apologize for the repetition, but I think it's serves a purpose. And thanks so much to both. Oh, now it's spoiling it. To Pavla and Oti for leading this exciting work in the high latitude dust research field. It's very impressive to see what you're doing, and it's such a pleasure to be part of it. So thanks a lot for having me also present today. Just to give you an understanding of the background for the work that we do in our department is that we have a special kind of role at our section in the Arctic Environment section, namely that we provide a lot of research-based advisory for the Greenlandic Environmental Protection Agency related to mining activities or mineral extraction activities. And that, yeah, you probably noticed over the last month with the new administration in the US that has kind of become a hot topic, and now they have an election in Greenland as well. So from our webpage at the came from 0 hits per year to 800 or so in 2 weeks. So it's quite. So some of the work that we do is quite topical at the moment, especially related to mining and environmental impacts from mining, but also maybe geopolitical aspects of that. So there's a lot of issues to that. But as you all know, then mineral dust can be made up of various kind of source materials and various grain sizes, and has different implications both for human health, for the environment, and for the climate. And our focus at what we do in my department is then for the environmental side of things. And the reason we are so interested in this is, if we look at this diagram here, we see on this axis from low to high emissions, and from the other from low to high hazardous risk, and then from low to high in the amount of dust emitted. And we can see that mining operations, and especially mine tailings, the very finely ground material, is up in the high red area. So that calls for special considerations in terms of how to address the risks and operations and the impacts, especially on the environment and on health from mining activities. And we know in Greenland there is a large mineral potential, a few legacy mines, a few operating mines now, but also an environment, natural environment that is highly emissive of mineral dust due to the glacial erosion of the bedrock under the Greenland ice sheet, and then the deposition of fine particles out in the proglacial domain. So you can see the top picture, that's a picture of the proglacial riverbed up in Gangslussvak, where we have natural dust emissions, and down here a mine in Greenland where, due to crushing and blasting and haul road trucking and all that, we have high emissions as well. They have different properties. The update that I'll give you today on the work that we are doing, the in situ collection work that we're doing, is primarily focused on these 3 sites here, or mainly 2, the Gangslussvak West Greenland site, and then Mestersvig, old legacy lead and zinc mine. And then we've done some work also in Advendalen up in Svalbard to investigate the impacts of in Svalbard is the coal mining, to see, okay, do we actually see an impact in the environment from both mining of coal, but also transportation of coal in a very highly emissive area as well. So, yeah, and the reason, just this is a repetition of some of what we've seen earlier, is also why do we care about dust from mining? Because, yeah, typically it can have high a higher than background concentration of especially heavy metals, And some of those can bioaccumulate in the ecosystem. And then, you have, especially for mercury, cadmium, not so much lead, but those other more risky heavy metals are of environmental concern and also for waterways and different. So, yeah. So just shown on a different map, this locations that we are at. So we can see we span quite also a climatic transect. And if we go and have a look at the Gangeslussuaq area on the west coast of Greenland, we can see that the ice sheet is here, the large proglacial plains here, and then we have three different monitoring stations where we collect dust either by active samplers or by passive samplers. And one of the ambitions of this work is also to investigate the sampling biases imposed by the use of different passive samplers that the mining companies usually do. Right? So it's to see, okay, is it actually a good approach that they do, or do they under or over catch? So these three different stations. The main one where we have power, that's a nice thing. We have a high volume sampler as well, and some dust track OPC, and then also some of these passive samplers where small weather station, one of these ARA pumps that they also use up at the Kluani Lake area, directional samplers, old school dust bucket, the mining company's favorite instrument, and then the dry foam frisbee samplers, that is a refined version of this. And we have those in the three different areas in increasing distance or decreasing distance from the ice sheet. So this is out in Sandfolkstaden. You can see the Greenland ice sheet in the back here, large proglacial delta. Then Midway, and then out in a location where you have more continuous vegetation, more representative of the general conditions in West Greenland. And the wind regime, you can see here, it's very much bidirectional, similar to what we see in many glaciated or mountainous areas, that you have these katabatic fall winds coming from the ice sheet blowing out towards the fjord system. And then when the conditions are right, you can have these massive dust storms and dust plumes. And here's an example from the 23rd of October last year, where I was there. And you can see out extending actually more or less 40 kilometers from the ice sheet all the way out to the fjord. You can see the fjord out here. You have these emissions of glacial silt, and I have some samples here that you can have a look at if you want to. Yeah, you can see some more pictures here. Again, a lot of dust being blown into the surrounding environments, and we are not really sure how the vertical distribution, or both the length extent and how it goes up, and if it has a bigger impact than just the near surroundings. But yeah, just some pictures from that. Yeah. So what we've collected so far is on the high volume sampler. It's been running continuously for 2.5 years now, with weekly samples, 13,000 cubic meters of air through one of these 15 centimeter filters. And you can see with different loading degrees, the ring out here, that's the unexposed, and you can see the coloration on some of the filters. Sometimes we have like biology as well. So it depends a lot. And then we have on other sample types as well. And the plan is to continue the high volume sampler for at least 3 years. The passive samplers, that is more for the methodological comparison. It doesn't make sense to, it's quite labor intensive to go every month to exchange samples. So yeah. And here's just some quick overview of the dust that we see. You can see that this is on the high volume sampler. We see in the spring we have the highest, corresponding very much to what also John Bullard and those people have found in the same area. So we see the same kind of pattern. What we're interested in is to see also the geochemical variation over the years, see if we see different signals at different source areas. And this is just the first year. We have one more year to add, and then another. So it'll be exciting to compile all the data in the end. So where we are now in Greenland is the main part of the chemical characterization is something that we're starting up now. We'll continue with the high volume sampler for at least, so we have 3 years. And then yeah, some more, assessment work. That's not so interesting for you, maybe. Some of the work that I would like to continue with is the vertical characterization of the dust plumes. And I see that there's another talk today about dust and drones. So I guess that's pretty much kind of the same kind of line of thinking. And we just purchased a new drone for that perspective also. And then we have another project coming up, which I call detailed. So that's emissivity of dust or particles from mine tailings. So using a laboratory setup, we can try to simulate or standardize the dust resuspension and then see how much with moisture and particle size and all that kind of stuff, how we can more come up with methods to stabilize that. And then we would like to do some field trials also with the dust suppressants on roads, haul roads, so we can see if that how that works. And that also links to some of the work that we've done with Songbo and Claudia on one of those Atmo Access grants that Songbo and we applied for. And then we did with this resuspension system sediment samples from these different sites, both from Antarctica, up from the Yukon, Slims River, different sites in Greenland and Svalbard as well, to look at optical properties and chemical properties and all that for the ice nucleating particles for that. So, and just because I didn't see it before I went to Lisa or to France this summer, this is actually the system, and we replicated that. So it's a shaker, vibrating shaker, and then a flask with some sediment in, a HEPA filter on top, an anti-static tubing, and then we can run it through different impactors onto filters or through OPCs or whatever, so we can characterize the emitted particles in a controlled environment, and then we can add moisture or dry it or whatever. Yeah. So, but this is something that we're also starting to work on in our lab in Aarhus University. Yeah, it's just a view at the PM10 impactor and the Svalbard dust. Another sample here, the most emissive material I've ever seen. It's amazing. It's one big plume. So I don't know. Do I have it?
You still have 10 minutes.
10 minutes. Oh, okay. Well, then I don't have to rush.
Not that much, but
Okay.
Yeah, sorry. Yeah.
Yeah, but that's okay. So that kind of gives you an overview of the reason we work in Greenland, what we've been doing, and what we would like to continue with. But of course, when we look at Greenland, you also saw that it's the geography. It's like a very large. So I'll just oh, that's the wrong way. Skip back to this is sorry. So this overview map here, because with the growing interest in minerals and base metals and rare earth elements from Greenland, a lot of different mining projects have been proposed, and one of them is up here at 82 degrees north in what's called Citronenfjord, this place here. It's one of the biggest known zinc bodies that they want to mine out and ship out. And it's located well within the Arctic circulation cell. So if we have things that are emitted here, it'll probably not be distributed out into a more global circulation. So it can have likely quite high local or regional impacts from this. And it also has lead and zinc and mercury and cadmium and those kind of trace metals in it. But the thing is to know, okay, how optimize a method in a place that is so remote that they can't even sail, most of the year. They have a window of 6 weeks a year that can actually go in. So we need some kind of analog methods or analog sites to study those processes and those conditions as well. There's another big molybdenum mine coming out maybe within the next 5 to 10 years in this area that has kind of the same properties. So we used Svalbard as an analog to the high Arctic Northeast Greenland side. So that's just to show you that, oh, that's the wrong way. Here we are. So in Svalbard, the reason we're interested in this is because we have a similar kind of glacial dominated ecosystem with high amounts of fine particles, mineral particles in Elven that is connected to the upstream glacier and glacial erosion. And also in this area, we have mining activities with haul roads and all that. So we have kind of the same overall parameters that we would expect in Northeast Greenland as well, although in a different, more maritime environment and different, mining activities and all that. But to understand the basic system on how much is emitted, when, which conditions, which environmental drivers, how do we actually in this kind of system quantify, if we can, the mining impacts. We set up this experiment here. So it's more or less the same methodology as in Greenland, directional samplers, dry foam frisbees, and then the low, medium volume battery powered collector, and then in some different locations. And there's more, and I think maybe Justine, the master student that's working on it this year, she might be presenting a little bit, but otherwise I have a poster here that I can put on one of the tables, and then we can follow up. Okay, so 2:30 is her. Okay, we can look forward to that. So I won't tell you more about this, except that we have things going on here and a lot of material that is collected. Yeah, these are more kind of if we have time, a bit of a bonus slides, but I can also skip it. Okay, so with the dust and the drones, the perspective, it's kind of a continuation of some of the work that I did in my previous work before I started at Aarhus University. We also had this drone project where this is a Matrice 600 from DJI. We have the new 350 RTK drone with different LiDARs and all that kind of fancy equipment on as well. But we're building an OPC sensor pack and remote triggered filter sampling device that can be attached to a similar drone, and then with an inlet outside the downwash zone. So that's we have, and then we'll build in some real-time data transfer as well. And just to see, with the right people, we have a good group of engineers at Aarhus University that can help us out with this. So that's really helpful. But you can see the old drone that we had was more for checking that the big ships are not using high sulfur fuel oil, like heavy fuel oil, right? So looking at the CO2 to SO2 ratio, you can see, okay, are they using the right stuff, or are they using the old the heavy fuel oil? And you can see there's the drone, and we have the flue gas or the smoke gas, and we have the sniffer drone there. And then what we can see is pre-programmed flights either within the ship, the smoke there, or in a dust plume in a natural area. We can pre-program both the X, Y, but also the Z direction, get real-time data, and then make something like this. It's a from figure with methane instead of particles, but it's the same concept with altitude, and then circle around this dust plume and might get some kind of 3D visualization. We both see concentrations and particle size, and also in the downwind direction, how far does it actually extend, and when can we see the particles settle out? That's at least the ambition for that. And the reason we think it's interesting is because if we have a big open pit mine, we would like to know exactly how much and where does it go and what's the impacts. And for that, before they start up with the big mines, we'll use natural environments to test and develop the methods and all that. So I think there's a good collaboration potential also with what I think your plans are for Iceland. So let's talk more about that. And then another issue, it's more local emissions, but with regional impact, is from most of the dust emissions from that we've seen so far from mines are actually from haul road transportation. So you can see there's two different pictures, one from the mine in West Greenland and one from the old mine road up at Mestersvig in West Greenland, where that dust that you see being emitted there has a lead content of about 500 ppm. So maybe 20 times 10 to 20 times the natural background due to legacy pollution in that area. So we have continuous redistribution of polluted sediment into the environment, and that can be used as a tracer to see, okay, if we apply some kind of dust suppressant to the road, it can be either biological or these polymers, biological polymers, or salt solution, or there are different commercial products available to see what works the best in this kind of Arctic environment. So we plan to go next year to do some field trials, spray the road in different sections, and then monitor with these low-cost OPCs also in a transect around, and maybe also with the drone to see, okay, how effective is it? So it's more of an applied focus. Yeah. that's what I hope that was useful.
Thank you, Christian, for the very interesting talk. And maybe there are some questions. We still have a couple of minutes. Yeah, so many people having questions. I think maybe Poyan was the first one.
Really excellent. So, I have one quick question. Typical diameters of these particles that are emitted to these, let's say, sources.
Yeah, from the mine.
Yes, that's.
Yeah, I think from the man-made areas, they typically grind it down to 75 micrometers, and then within this flotation, I don't know if you know that, but water bath, and then you get a.
But on the surroundings, you cannot treat it, not mechanically treated, which are the diameters of the surface.
Yeah, okay, the natural surfaces. Yeah. I don't have the data yet from this Svalbard one, but from the Greenland, we have a lot of material from different glacial outlets, and it is 5 mole. So some of it is in the very fine fraction, maybe 1 to 5 micrometers, and then the second fraction is maybe between 30 and 50. Something. And then of course we have a lot.
It's much brighter than it's here in Iceland or other. That's my
second
really question.
Oh yeah. But you can pass this one around. But this is it's nice. Primarily in the West Greenland region, the bedrock there is primarily nice, like nice. So it's suitable.
Sorry, I'm not sure if the remote participants can hear the questions, so to keep them also involved, I will bring.
Yeah, I forgot we have another microphone here
Okay.
for the question.
Okay.
Sorry.
Just okay, good.
Was there another? Hi, welcome. Actually,
Oh, thanks, Christian. It's a really nice study and many interesting for me issues to further discussion, so we can continue. The last slide you mentioned about mitigation. It is very important to do. And of course, for transport emissions from surface, it's clear way. What about other type of main sources of mining from tailing dams, for example? How you expect and did you analyze a way how to minimize dusting processes?
Yeah, that's a very good question, and especially the mining industry is moving towards. You probably all heard about the dam failures in Brazil. Huge dam failures where a lot of tailings washed into the Amazon rivers, and so the industry as a whole is moving away from doing slurry deposition to dry stacking of tailings. And when you deposit it dry, then you have the dust erosion problem. So it's really a very topical question that you ask, and that's one of the ways is the typical way that they use it now is by moisturization, right? So they spray water on and then keep it damp and then hope for the best. That's kind of You can also cover it with plastic linings and that, but for larger facilities, that's not really something that is widely used. We see it some places where they have very high, in Canada, for instance, where there are very strict regulations. But it is one of the focus areas, especially in the new way forward for the mining industry to dry stack it. And one of the projects that we would like to work with that I didn't show you today, but that's something that's discussed also within the industry, is to do calcite precipitation. So you make kind of like a geogenic crust using enzymes and urea, and then you can produce calcite within the grain. So you kind of like do a geological stabilization, and that works. In some areas, we haven't seen it in the Arctic yet, but the problem with that method is that you use urea. So you have ammonia, as a byproduct in a very nitrogen-starved, environment. So there are different environmental impacts from that as well. But it looks promising. But the other thing could be molasses or other things that you could temporarily during operations cover it in, that is biodegradable, and then that could limit the emissivity. But that's what we would like to use that shaking device for.
Okay. That's also one of the issues what I would like to discuss, because we have long-term experience with such issues, and tomorrow I'll say about the way how to minimize and mitigate technogenic dust sources.
Perfect.
Okay, thanks.
Fantastic. So we are running out of time, so very quick one.
Yeah, thank you for your interesting presentation. I just wanted to know if you, I missed a part of your presentation. You had some talk about the Kuluani Lake region. Are you already done the dust collected dust from that area? If yes, I just would like to know more.
I haven't personally been involved in the dust collection there, but James and Daniel and Arnold have are heavily involved in that. So I guess they will be presenting that. Yeah.
Okay,
Thank
we
you so
can
much.
continue discussion. There is also one question in the audience. So regarding how do you think that the drone will survive in dust storms?
That's a good question.
So,
we hope it will.
Yeah, so
Yeah.
hope is there. Okay, so then it is, yeah, thank you, Christian. Yeah, excellent. Then we will continue, and our next speaker is Silvia Pecatli from Italy. It is so nice to see you.
Hello to everybody.
Fantastic. So
Hello.
hello, and yeah.
I'm really sorry. I'm not there, but anyway, I try to show you something, some
Yes.
results. Can
Yes.
you see my screen?
Yes, we can see your screen. So welcome.
Yeah, and
your-
now is in
It's-
presentation mode.
Yeah, we will
No.
wait a second. It will.
Yeah.
Yeah, now it is. Yeah.
Now it is. Yeah.
Okay, you are ready to start then.
So ready to start. You can register me if you want. And yes, go on. I'm presenting a study about the chemical composition of dust deposited on the surface snow in northern Greenland. The study was performed last year in March. And the sampling site is in the northern Greenland and Thule High Arctic Atmospheric Observatory, which is a study, a site for aerosol study and also physical properties of aerosol and snow. The aerosol collection started in 2010 and is continuously running. But last year we make a collection of snow. We collected the first centimeter of snow and in clean condition, and we collect for several analyses. We collected also some soil by covering the soil by the snow, and we proceed with soil by putting in the water and collecting the over part of the solution, which is not a solution, but there are some dust dispersed. This is not the best way to collect a soil sample for analysis, but this is what we can do on site. Then we met the snow and we filter on polycarbonate on field. And what we can see is that filters are not white as we expected, but filtering about 200 milliliter of snow, we can see in the picture that we have a light color deposit on this filter. And this is the first surprise for me, because I was thinking that snow is apparently white and there are no particles on the very most superficial layer. So we performed the chemical analysis on this filter, on the soil filter, a digestion in microwave oven in nitric acid and hydrogen peroxide for elemental composition by ICP-AES. And we measure also ions in the snow, but I show you mainly result from metals and elemental composition. There are also samples collected for SEM analysis. SEM, what show that the particles collected over the snow are typical dust, mainly feldspar and clay, but there are also the atoms. So this is a very surprising result, but this is what we observe. Regarding the comparison between snow and aerosol, we calculate the dust content by aluminum content, knowing that aluminum is about the 80% of crust. So in this slide, I show the PM10 measurements in red, and the dust content in the aerosol, which is the blue line. I don't tell you that we collect aerosol at 48-hour resolution. So every sample is representative of the average of 2 days. And in the dots, the blue dots are the dust collected in the snow. We can see very similar pattern. When snowfall occurs, so we have a drop of concentration on the snow. So this is preliminary result. I was thinking that it will be a dry deposition of dust. And I confirm this result by calculating the flux of dry deposition by aerosol measurements, considering the position velocity of aluminum and therefore dust of about 1 centimeter per second. In this way, I calculate the only dry deposition that is possible from the dust concentration in the aerosol. And this is represented in the picture by the continuous line, the step line. I can calculate also the real total deposition by the snow, by the dust in the snow. And this is the dot in the line. We can see that there is a very, very nice agreement, also considering that this approach is very approximate, because the uncertainty of aluminum deposition velocity, and also by the sampling approach. But we can see a very, very nice correlation, except for a sample of fresh snowfall. The fresh snowfall is characterized by very low concentration of dust. This is because of its mainly mechanism of deposition, because it's arises from the composition of the cloud, essentially. But in absence of snowfall, we can see that the dry deposition is the dominant deposition flux. So the next step is, where does dust come from? And so we make a preliminary approach by comparing the soil collected, the composition of the soil. These are the main components, so silicon, aluminum, iron, titanium and phosphorus. And we can see that especially the ratio between aluminum and silicon is quite different from the dust collected on the snow and the soil collected around the observatory. We can see also that aerosol the composition of aerosol agree with the composition of the dust collected on the snow. So confirming again that the dust deposited on the snow arise from aerosol. Another evidence is that the titanium aluminum ratio. The dashed red line represents the local soil collected, as I tell you before. And also in the same way, we have the titanium aluminum ratio in the dust on the snow and in the aerosol. This configures the higher than 0.07 arise from local source. On the contrary, lower titanium aluminum ratio are present in different kind of dust. Rare earth elements help us to recognize some source area, but actually result on rare earth are very difficult to interpret because they have very, very low concentration in the aerosol. So the aerosol data are less characterizing of this ratio. But anyway, we can see a large dominance of light rare earth elements with a larger dominance in the snow respect to the soil collected in the surrounding area. Regarding other elements, we can see that aerosol is enriched in particular elements that arising from anthropic activity, and especially arsenicum, cobaltum, lead, and copper. And especially the ratio, the nickel-aluminum ratio, is a sort of fingerprint of dust source coming from Greenland, but from the southern part where mining activity on these elements are active. So both from aerosol and with less evidence in the superficial snow dust, an enrichment of nickel is observed. And this enrichment is especially high in the aerosol. This is because probably is in the finest part of aerosol, which is not deposited at the same velocity of aluminum and properly dust.
2 minutes, please.
Yes, I finished. I have just the last slide, but this is very preliminary result on the effect of dust deposit on the snow and the albedo. We can see that especially when we have the very high dust content in the snow, up to 1 milligrams per liter, we can have a shape in the visible part of the reflectance spectrum that is very different from those from superficial snow when collected when we have a snowfall. And we have in the infrared part a different shape with very low reflectance when we have a different shape of snow due to the snowfall. So what we can learn from this is that, and the conclusion from this study is that particulate deposited on snow in March in last year is essentially dust. Dust is not arising from local source, but probably could arise from southern Greenland. Dust on snow is mainly dry deposited, and which is the very important effect on albedo, that when we have a very high concentration of dust, we can have an effect on the albedo of the snow. So the work are in progress, and especially next campaign, we performed several other measurements, and we deep study this conclusion. So I finished. Thank you for your attention.
Thank you, Silvia. Do we have questions for Silvia here in the room? Yes, Christian. Yeah, we will give the microphone to Christian.
Oh, wow. Yeah. Hello, Sylvia. Thank you very much for the very good, nice presentation. And
Hi.
there's so many things that are, interesting for the work that we do also with the. So first, one comment, once we have the geochemical results from the high volume sample at the West Greenland, Mid-West Greenland region, I'll be happy to share it with you so you can see if you can confirm the hypothesis that it is input from southern latitudes. Another question, are you in contact with Philippa Huntsman and those people that are working up at the Mary River mine with the dust monitoring and dust characterization in that area? Otherwise, maybe they can actually provide you with chemical data for the sources of the mining and natural environments in that area that you can compare to the sources that you see.
Yes, when I see your presentation, I see I need this dust.
Okay.
Compare, because we have a soil from Thule, but it's more interesting to have a more complete, but especially aerosol is important because, and we are interested if you have sample to compare our results with yours. Yes, surely, sure. This is very, very important.
Then we have online question. So Santiago Gasso is there. Hi, Santiago. And asking, with your equipment, can you confirm or check if smoke or dust from long-range transport, for example, Canada, deposits in Greenland?
Yes, we have data, and we have a lot of signature of this area, the North Canada. Not last year, but we have more than 10 years of measurements, and in especially we have evidence of fire, of forest fire aerosol arising especially from Canada, and also heavy metals arising from the same area, and polluted area, also in southern part of Canada. Yeah, yes, we have. Yeah.
Yeah. Okay. And there was a continuation from Santiago Gasso. Do you plan to collect samples at other times of the year?
Yes, we have aerosol is continually monitored. Unfortunately, for the snow, we don't have people that continuously can collect snow in at high resolution in winter, but we have bulk snow collected this year, and we plan to collect continuously, but is only a mean values for all the winter when we put the collection funnel. Yeah.
Okay, yeah, and that also replies to the next question of Myers Ayon. So is there a plan to sample at different season than March? And then we have Jim McQuaid, who asks, we collect surface samples and aerosol at site 1,100 meters, 50 kilometers east of Kanger. A significant portion was local source. This was from rare earth provenance analysis. So that was for your, and there is this UK Black and Bloom project, so, and with the link as well. So thank you, Jim. Okay, we have one more question in the room, so please go ahead.
Sorry, just had a quick question. As I understood, the dust, the snow samples was just 1 centimeter. So could it be just, as it is just 1 centimeter, we can call the dust, deposited dust as a local dust? Because I'm not aware of how the snow is in that area, but just wanted to know, as it is just 1 centimeter, could it be Asian dust coming there? But most likely it is a local dust, because it is just, you sampled 1 centimeter of the snow, and just had this question.
Maybe I can have a comment. Maybe I can have a comment in general.
I'm not sure to have understand, but the height of the snow is actually high, about in some place about 30 centimeter. I collect just the first one, but there are some areas uncovered by snow, because in this sampling campaign we have a lot of strong wind. So my first idea was that dust is from local source, because there is strong windy, and some areas are uncovered. And yes, for this I think that it could be local, but in summer we have evidence only by the aerosol, that we have evidence that local dust is quite important in the aerosol load. Yeah.
Okay, thank
Thank
you,
you.
Sylvia. I just continue shortly about this first centimeter collection. So when we had Saharan dust in Finland, we also collected only the surface snow, but there the event was such that dust had been long range transported from Africa, and it was in different layers in the atmosphere, and once we had a snowfall, it just washed out all that remote dust that would not have landed otherwise, but the snowfall brought it down to the surface snow. So it is possible that it can be also remote. Yeah. Okay. So thank you very much, Sylvia. It was so nice to see you here. Okay. Then yes. Sorry.
Yes, I'm here again. If you want, call me, tell me something. Don't worry. Okay.
Okay. Thank
So,
you.
bye.
So,
Go on.
Bye. You can stop sharing now, please. Okay. Our next speaker is Daniel Bellamy from Canada. And his talk will be about measuring and modeling mineral dust from Canadian proglacial valleys. So Daniel, the floor is yours. You can share your screen, please.
All right, how's that?
Yeah, we see and hear you fine.
Perfect. Alrighty. Yeah, hi everyone, good morning. Today I'm going to be sharing some highlights really of about 4 projects based on our work, both sort of with in-situ measurements in some of these Canadian proglacial valleys, and then moving also to this modeling approach to try and understand the big picture. Yeah, so what I'm going to take you through today is, first I'm just going to overview the study region, give you some context, and then we're going to look at these 4 different projects. So first we're going to investigate the wind mechanisms that happens in these complex terrain and try and pin down what are the meteorological processes driving strong wind events here. Next, we're going to break down the surface erodibility. So what are these interspersed surface controls that we conventionally get in proglacial valleys, and how does that really sort of limit when we can see dust, and what's that window for emissions look like? Then once we constrain those two, it's a movement to the parameterization of the dust emission process itself. You know, how well can we parameterize the physics of that? And then lastly, bring it all together. Then can we implement a modeling approach, tie all these things together and generate sort of regional estimates for these sources. So we're focusing on these interior proglacial valleys in the St. Elias Mountains in Western Canada or Southwest Yukon. As you can see, we're on the leeward side of the St. Elias Mountains, and really there's a huge sort of climatic shift over this about 170 kilometers from coast to the interior. You go from like getting 3 to 5 meters of precipitation on the coastal side to about 300 millimeters of precipitation. So you transition really quickly to this semi-arid source. So here we obviously have these proglacial valleys fed from this huge ice field, fed from the St. Elias Mountains, where we're going to be looking at all our stuff. And of course, there's dust in these places. There's always the photo tax to be paid, but these are dusty places. So first, the wind mechanisms. The question is really, yes, so if we want to predict dust emissions here in moving forward, what atmospheric phenomenon do we need to ensure that models are getting to make sure we can simulate these high wind speed events? So yes, let's determine these meteorological mechanisms. But how are we going to do that? We have some service meteorological stations, and we're also going to do some numerical weather prediction modeling to help us along. And this was in a recent publication in Journal of Applied Meteorology and Climatology. So first we have this indexing approach. So we have these surface stations. And what we do eventually is identify the characteristics these wind systems should exhibit. So for example, if we're expecting a katabatic or off glacial wind, what are the conditions that we need to see that? How can we cross off other potential mechanisms? And really, to summarize briefly, what we really find is the majority of high wind speed events in the valley over a period of about 15 months, it's synoptically driven. We're seeing that these synoptic configurations differ from those driving emissions from the coastal Alaskan sources. So they're really happening at different times. We didn't find any evidence of off-glacial winds driving high wind speed events, and really there's more of a signal of local wind systems. They're increasingly apparent in summer that we see driving high wind speed events even under sort of calm synoptic conditions, and especially sort of near the lake, we get a lot of nocturnal emission events. So from like 1 to 6 a.m. in the morning. Yeah, so we have some more modeling that supports that, and we do see these evidence of some up valley flows from adjacent valleys. And then obviously we can build a picture of how does the force channel and synoptic flow look in these valleys, and what are the different wind regimes we expect under the two different conditions. So after that quick overview, then we're considering surface erodibility. So what are the landscape controls that we see in the proglacial valleys, and what is this window for dust emissions here? And in this case, we're most interested in camera stations. We have several time-lapse camera stations that we can use to constrain dust activity qualitatively. But then in terms of diagnosing surface controls, we're interested in a remote sensing approach. So it's using Landsat retrievals 5 to 8, and then MODIS retrievals. So first we can characterize the emission activity based on the photo records. And we do, so this is a record from 2016 to 2022. And we can characterize dust emission activity, so we can understand approximately how many events we're seeing from these valleys. And also, based on a visibility reduction, get a qualitative estimate of emission severity. And we can see this really significant annual variability. So for example, 2018, it was going. We really saw more major events in 2018 than a lot of the other years combined. Next, we can characterize the landscape control. So here we've done, based on Landsat indexing, we can assess meltwater coverage in all of the years. So this is what we've indicated in this figure, but we're also interested in, obviously we want to know what surfaces are getting inundated, where there's going to be deposition, but secondly, we're interested in, okay, but where subsequently exposed. So where are the surfaces subject to regular inundation in summer, and then exposure and availability for alien processes. And we see about 83 kilometers squared of these surfaces. So flooded in summer and exposed in autumn, and sediment texture notwithstanding, available for alien processes. Next, we also evaluate the snow cover. So this is based on MODIS retrievals from 2001 to 2023. So we have daily cloud gap field data. And again, so we can characterize sort of the climatology of snow cover in these areas and assess the variability, really to constrain where that window of emissions can be. But secondly, also that we see spatial disparity between these locations as well. So for example, there's about 35 days, roughly, of snow cover disparity between the least snowy and the most snowy valleys in this region. And then we can sort of combine all this historical knowledge and then add in sort of all these predictions we have from the cryosphere fields and predict or make a conceptual model of what's going to happen to dust emissions in the near future. So we're anticipating widespread loss of the cryosphere over various time periods, depending on how big the ice system is. So for the ice fields, especially in the St. Elias Mountains, they're rather big, so there's still the loss of the cryosphere is accelerating. So we're essentially anticipating an increase in meltwater discharge over the next couple of decades, which is really going to translate to an increase in this transient sort of erodible area that we can get before obviously subsequent decline. And we'll see obviously how the glacial loss plays out by the end of the century. But obviously with this decline of meltwater and this flattening of the hydrograph, we're generally seeing the surface stabilization. So a stabilization of the surfaces that are normally kept erodible based on these meltwater dynamics. Great, so those are the two big sort of controls, and now we can focus in on looking at the dust emission processes themselves. So specifically where we've got our tower is situated on some glycogenic sands. The question is really how effective are the parameterizations for simulating dust on these deposits? And how are we going to do that? So this is a straight sort of tower micrometeorological approach. We've got we do an array of sediment sampling just to characterize the deposits. Then also we have an assessment of siltation and dust fluxes based on OPC measurements. And just to characterize sort of two things, this is in prep. First, we look at sort of spatial variability. So obviously you can see from this image, it's on this sort of oblique image from drone imagery, where you have sort of this development of sort of active sand, small protodunes, spills, so, deflation lag. You've got exposed sort of silt laminae sort of characterizes these depositional faces. And obviously, if you have this heterogeneous sediment sampling, we see different sort of siltation PSDs. We see differences in siltation activity. So the question is obviously, if we've got this heterogeneity, how to parameterize dust production processes. And this is still in prep, but what we do basically is we grab a lot of common dust emission parameterizations and emission parameterizations used in high latitude dust modeling to date, and we see basically how they compare to our in situ observed emissions. And there's a mostly good agreement. There is some sort of discrepancies we highlight, and I won't go into it here, but there's also some, what's the implementability of these schemes? And this is really important, obviously, because all our high latitude dust estimates are sort of solely based on modeling at the moment. We don't have this observational global crutch. So that can be worth noting I've seen some approaches that will then tune dust emission modeling based on the previous efforts of dust emission modeling, which is really sort of constraining how we constrain high latitude dust dynamics. And then lastly, quickly, obviously, combining that all together, can we simulate dust emissions from these valleys now? So what we're going to do is we're going to implement a model approach and evaluate the meteorology, which is obviously critical in this mountainous terrain, but also the emission dynamics themselves. And to do this, we've used a regional WRF modeling approach. So we have a couple of domains as indicated here over these proglacial valleys. And we have a few simulations we run. Just to highlight two things, if we look at sort of meteorology, so this is just the meteorology comparison in summer, where we compare the wind speed distributions. Generally pretty good performance for the model, which is really encouraging, obviously, because we're in pretty complex topography. The valley is only a few kilometers wide, and it's got sidewalls of like 1 kilometer high. If we look at sort of the dust scheme, when we do a comparison based on the station data, again, we see pretty good agreement, but there is some sort of the dust scheme we implement has a lot of sensitivity to sediment texture. So especially across the delta, where we go from these sandy deposits to these sort of fine silt and clays that you mentioned, where obviously we see a lot of sort of order of magnitude differences between that. So it's a bit problematic given for a lot of these sources we don't have sediment texture maps, or they just don't exist. So here's obviously the summary of the dust emission fluxes that we see up top, and then obviously dust concentrations below to get a feel for the dispersion of this material. So in this approach, we use sort of real-time inundation conditions, and we have different erodibility costs as well. So we try and take into account gravel cover and the influence on shear stress partitioning. And our estimates we generally come up with is about 16 tons per kilometer squared per day, not kilograms, across the surfaces. And obviously in terms of dispersion, we're seeing dispersion up the glacier. We're seeing dispersion sort of over some of the side valley walls, which is over 1 kilometer in height. And then from the delta itself, I'm not sure if you can see my cursor, we're seeing a lot of dispersion northward up the lake. So just to summarize quickly. So from that first section, obviously we found that synoptic forcing and mountain boundary layer dynamics are pretty responsible for the strong wind events here. We then characterized this interannual and also inter-valley variability and erodibility conditions. and did this look forward to the near future changes to aeolian processes in proglacial regions. Based on in-situ measurements in Chapter 3, we scale up emissions from the delta, and we find that over the 25-day period, we have about 390 tons of dust emissions. And then in Chapter 4, when we then model everything, we find that we're able to implement a successful model for this topographically confined proglacial valley, which is promising. But at the moment, it's representative surface characteristics, which are the largest channel. So we can pretty much get the winds, and we can get the winds from other products as well. It's just obviously constraining these heterogeneous deposits and making sure our emissions are representative and accurate. Awesome, thank you.
Thank you, Daniel. Excellent. So there is already one question, like clarification. How do you decide whether synoptic or local basin dynamics control a given dust event? So can you open that a bit? Yeah, thanks.
Yeah, so in that index approach, so basically we identify thresholds. So we, based on sort of a study of the literature, we say at this height, like at a given wind speed, it's going to be synoptic forcing that's dominating any local wind forcing. So in that indexing approach, we specifically say at 10 meters per second at 750 HPA. At that point, based on all the literature we've reviewed, it's not likely that local wind systems are existing that are unmodified by that synoptic forcing. So the balance of probabilities, it's synoptic forcing that's driving. Then under calm conditions, we then try and identify the signature. So do we see the signature of a glacial wind in these spatial meteorological stations? You know, do we see the conventional sort of valley dynamics in terms of the diurnal cycle?
Oops.
So
Thank you, Darren.
the person who asked, was this okay, or do you want to ask more about this? I guess it was okay because he shut his camera now. Okay, so it was good. Okay, then we have also from Santiago Gasso. We have Alexander Gurgansky first. What is the horizontal resolution of your WRF simulations?
600 meters.
Great.
So pretty fine scale, and we obviously use we start to use some scale-aware turbulence parameterization to try and account for that.
Okay, and then Santiago Gasso, in terms of a big picture, can you compare the dust emission scheme in these valleys with the one you would use in lower latitude, say Sahara? Main difference.
Yeah, so it's still a bit of progress. At the moment, it looks like the magnitudes are stacking up pretty well. What remains to be seen is obviously a lot of these schemes can scale quite dependently on clay content, but there's some recent work obviously looking at the different production mechanisms we might see, particularly over sort of glaciogenic sands. So I've got a little bit more work to do, but for the moment, at least the magnitudes are comparing okay, but then that was just a 1D model, and it's when we start to sort of account for, you know, these mass sediment texture differences, we might see a lot more scheme dependent variability.
Okay, so thank you very much again, Daniel. Great presentation. Okay, and then we will continue to the last speaker of the session one, who is Polly Foster from UK, and the topic is dust drone, aerial sampling of dust plumes over Iceland. So this is interesting, as we already had one question from the audience for Christian earlier. So how do you manage with drones and dust storms? So Polly, the floor is yours, and welcome.
Great. Hi, everyone. Yes, I'm Polly Foster. I'm from the University of Leeds, and myself and Ben Pickering from Menapia are going to talk through a project that we did last October now with Pavla as well, as you will all know Pavla. So the project is Dust Drone, the aerial sampling of ice nucleating dust plumes over Iceland. And first I'll go through a bit of background here. So ice nucleating particles are sort of aerosol particles that can initiate the formation of ice crystals in the atmosphere. These particles are often dusts, mineral dusts and soil dusts, as well as different biological material, sort of pollen, bacteria, even viruses, as well as the smaller constituents of these, including things like macromolecules. So Icelandic dust has previously already been shown to be a source of INPs. These measurements here were taken by another PhD student at the University of Leeds, Alberto, and these were filter measurements taken from the FAM aircraft, which is the UK's atmospheric research aircraft. And some modelling work that Alberto did showed that Icelandic dust can dominate the low latitude dust sources at certain altitudes. So one thing that we wanted to do was to delve in a little bit deeper and try and look at the vertical extent of some of this dust and see actually how far the Icelandic dust can make it up into the atmosphere and how good it is in acting as an ice nucleating particle. So the actual campaign itself was funded by the UK to Iceland Arctic Science Partnership Scheme. And this is a Natural Environment Research Council Arctic Office funding. And it was a proof of principle field campaign where we utilized a sort of unmanned aerial system, a weather drone, integrated with different meteorology sensors and aerosol sampling equipment as well. And this image here just shows the sort of the experimental team, which were part of the measurement campaign out in Iceland last October. So I'll quickly just discuss the two aerosol sampling pieces of equipment that we had on the drone. So firstly, we had an electrostatic precipitator, and this has been developed by the University of Hertfordshire. And this instrument works by charging aerosol particles, which are drawn through the instrument using a fan. These charged aerosol particles are then collected onto a removable collection slide. And this is just a standard glass microscope slide, which can then be kept and used for multiple different analysis techniques. And then we also had a OPC. The one we used in the end was the AlphaSense OPC. Originally, we wanted to use a University of Hertfordshire modified open path OPC, but due to some data logging issues, we went back to the traditional one. But for future work, it will hopefully be the open path OPC that will be used. And now I'll pass on to Ben to talk more about the actual drone itself.
Thanks, Polly. If I can get a thumbs up from someone that I'm heard, that would be good. Great. So yeah, my name's Ben. I'm from the company Manapia. It's a small company based in the UK, and we really exist to sort of take the headache out of drone operations. So we develop and build our own drones. We modify existing drones. We can do a range of payloads. We do field campaigns, and long term, we desire to have automated charging on the ground, so we don't need any humans on site, and we can do longer term campaigns. So for this particular pilot project campaign, we needed a bit of a heavier payload than we had on the drone we built ourselves. So we opted for a 2.7 kilogram lift payload drone, and there's an image of it there, and I'll just walk you through the different sensors. So the electrostatic precipitator on the left-hand side there, that Polly just described. We have a sonic anemometer from Lycor. It's actually a 2.5D sonic, but the way we mount it vertically and then we rotate the drone to face into the wind makes it a three-dimensional measurement. So we can get good vertical winds as well. And the turbulence spectra is particularly good from that sensor at 40 hertz. The photo here shows the modified open path OPC, which University of Hertfordshire kindly lent us for this project. We did have a slight issue with that though, so we had to revert back as Polly just mentioned. And then on the underside of the drone, you can see a white box there, which is just our data logger and flight controller software that runs on it. And the two white pods on the legs of the drone are our in-house built MET sensor. There's a photo of that on the right-hand side just showing how we use the propellers of the drone to aspirate the sensors. It's around 10 meters per second of aspiration, our best estimate. We have very fast response time because our main concern is to do good vertical profiles. So we have a 0.3-second response time for humidity, and this sensor has a 4-second response time for humidity, for temperature, sorry, but we are currently working on a new version that has a 0.1-second temperature response time that we're really happy with. Some upcoming modifications to how we mounted this. This was just a fixed axle for the electrostatic and the OPC instrument. But in the future, we would like to have a rotating axle. Because the drone turns to face into the wind, it'd be good if this horizontal axle also like pitched up and down, so it matched the incoming wind that we measure on the sonic anemometer. And we've got some upcoming projects that will be mentioned at the end that will conduct that work. Next slide, please. Part of the reason that we can do these campaigns really effectively is that we maintain the airspace permissions across multiple countries. So at the moment, we have permissions in Iceland. We did have permissions in the UK previous years, and we've done flights around Europe. You can see all the different locations on the map there. So we maintain that like expertise in having airspace permissions. And this is transferable across countries. So compared to research groups within universities, the headache they have is that one person might go and do all this work, and it is quite a lot of work to maintain the regulations. And then if they leave the group, then that knowledge and skill is lost, and it's hard to maintain that. So we exist to sort of maintain that skill as a service. Some of the location on here, you can see we've got a column of routine airspace that we use in the Snæfellsnes Peninsula in Western Iceland. That's 6 kilometers. And we're about to do a 1-month demonstration campaign, actually, where we do 24/7 per hour operations there. So we're quite excited about that. The gray sites here are like hopeful upcoming locations that we're intending to do some work in Greenland as well. So we've also done ship-based campaign work in the Mid-Atlantic last year with TU Delft. So that was particularly exciting. And the next slide just shows a little holiday reel, I suppose, of the campaign that we did. Hopefully the video works. Great. Yeah, so we were out there for 5 days in mid-October. This is one of the glaciers that nearby to our location, and it's extremely beautiful, of course. We were actually chasing dust plumes that we could see across the desert on this day, but by the time we got there, they'd subsided. So we decided to try and do some sampling near to the glacier instead. Later on that day, we Polly had the suggestion of trying to do some biological sampling because these moss-covered mountains are particularly striking, and there was a potential science to be done there. And then our main site for this campaign, which had a 2-kilometer airspace, was Mira, and a very kind farm owner allowed us to use their land that week. And this is some onboard footage of us flying above cloud. We didn't deliberately fly into clouds on this campaign, but at the very end of the week, we had one flight through the clouds there, which were icing clouds. And then there's just a few more shots there of the setup and the work we did. Yeah, so we did, some high altitude flying there, carrying all these sensors. And I'll hand you back over to Holly now to discuss the results.
Great. So if you just give me a second, my taskbar is in the way of switching the slide. So I'm just going to move on manually. Yeah, so after that very exciting 5 days in Iceland, I had the task of taking all of the collected aerosol samples back to Leeds University to do some cold stage analysis, which is one of the instruments that we use to detect ice nucleating particles. So I drag a small microliter droplet across the glass slides that I showed earlier from the electrostatic precipitator, and then pipette this aqueous solution of aerosol into lots of different droplets, and then slowly ramp down the temperature of these droplets, and they subsequently freeze, and you can see them freezing here as the droplets turn dark. And then from this, we get a fraction frozen curve, which is the number of frozen droplets. Yeah, the fraction of frozen droplets out of the total. And then using this, we can then get a concentration of ice nucleating particles in the air volume that was sampled. And the preliminary results of these, I apologize for the quality of this figure. I thought it was better than that. But the preliminary results here show fairly low activity in most of the samples, sort of -15 and below, mostly below -20. And this is consistent with what we see in a lot of mineral dust samples. This is consistent with previous measurements done by Alberto. And I think something that is important to note is that we also took handling blanks, and this is measurements done like without turning anything on, just to make sure that there's no contamination. And most of the samples here were above that, which shows me that this is a technique that we can use again into the future. So I'll just leave the summary up here, the summary and future aims of this project. So I think the big conclusion that I made from this project is that aerosol instrumentation can be integrated onto unmanned aerial systems for atmospheric profiling and sampling of atmospheric aerosol relevant to ice nucleation. And there's a few more future projects that will hopefully be completed and accepted as well. So I'm working with an undergraduate student at the moment who's investigating the effect of wind speed on the electrostatic precipitator sampling efficiency. And Declan Finney at the University of Leeds has a fellowship proposal under review with Menapia, and they're seeking to do work using the OpenPath OPC to look at the cloud-based droplet concentration. And I've left Declan's email there if anybody does have any more specific questions about that kind of work. And then there is plenty of potential for similar campaigns, as well as repeating this campaign, but with the ultimate goal of measuring within a dust plume, which is what we aimed to do originally, but unfortunately, they all dissipate fairly quickly. So that's pretty much everything. And thank you very much. And yeah, I'll take any questions.
Great, thank you for the amazing presentation. I see there are many questions already in the chat. So first of all, Santiago Casso, have you characterized the collection efficiency of the inlets, and what is the maximum wind speed that the drone can operate in?
So I'll take the question about the efficiency of the inlet. So that's work that University of Hertfordshire are currently working on. It's with the way that the charging works within the instrument, there's quite a lot of things to take into consideration. However, previous work that I've done has been comparing this electrostatic precipitator to a more commonly used filter sampler that lots of different groups would use to collect ice nucleating particles. And from my work there, they show pretty excellent agreement in what they measure. So I'm quite confident that this instrument is collecting most of the ice nucleating particles in a sample.
For the wind speed question, this particular aircraft is quite large and sluggish, so it's only got a wind speed rating of about 20 meters per second, which is still, fairly okay. The one that we build ourselves has a 25 meters per second wind rating. That's if you're sort of just hovering or ascending. However, there's a plethora of other UAVs that can do faster, and I think it's important to bear in mind this was just a pilot project. There's lots of improvements that we'd all love to have made, but in the time and the funding we had available, it was just a pilot project. So the aim is that in the future we can have these sensors more well integrated, more streamlined, lower the drag on the UAV, and custom UAVs could get to much higher speeds. So that would be a future engineering project.
Great. Then there is a question by Hugh Brenot. Up to which altitude can you bring your drone and for which payload?
For which what? Sorry, I didn't catch the end of that.
Payload.
Payload. Again, a very complicated question with the payload in there. That particular aircraft can go up to it's 5 kilometers with a certain propeller, and then 7 kilometers with a different propeller. When you introduce payload, it's a non-linear curve of change. The wind conditions matter as well, but generally I'd say 6 or 7 kilometers is the current maximum altitude you can reach realistically. However, we do now have a patent pending to descend by essentially letting the drone free fall and having only control in the horizontal, which is almost doubles our battery life. You'd need to have variable pitch propellers for that to go to the lower air densities, but that's a really exciting thing that we haven't actually talked about publicly until right now. So breaking news.
Okay, thank you. Then we will have a final question from the room here. So Christian Jørgensen.
Yeah, well, thanks a lot for the very inspiring presentation. It's more of a comment than a question, but it seems like I would be reinventing the wheel by making something similar, and you have a way head start, and that's really super impressive what you do. So I'm just thinking how to find a way to get you guys to Greenland and actually do the same kind of profiling. That would be excellent. Thanks.
Yes.
Great. Yeah, no, that's what we want. So the 7 employees that work at this company, we all come from research backgrounds. Mine's meteorology. The rest of the team are mostly engineering backgrounds. So we wanted to, have this solution. There's an email address that's currently cut off by the taskbar on this presentation, but I can leave my email in the chat, and just reach out to me and we can have an informal chat.
Great. I saw you had 2 locations in Finland as well. Were they with FMI?
Yes.
Pallas and some other place.
Jokioinen and Pallas.
Yeah. Okay. Yeah. Great. Thanks a lot for your great talk. Very interesting. Okay, so then there is one final question. Will these recordings and talks be available after? So Pavla knows this. I would assume so.
Yes, I will answer this. It will be available on the website of Ice Dust Association, the icedust.com, but maybe within a week, not exactly today or tomorrow.
Yes, so within a week or so, yes, in the same webpage as all information, icedust.com. Okay, so thank you everybody for the first session. Pavla, is there something general or do you want to wrap?
Yes, thank you everybody. And so we will stop recording and we will meet again at 12:45 Icelandic time. Thank you all for the contributions.
Great. Thank you all and see you in session 2 and later on.
And for the persons in the